All right, so welcome to the spring semester. A little bit chaotic, but a lot of you are used to this from the previous semester, so it won't be that big of an adjustment. And heck, you didn't even have to get out of bed hardly this morning, right? You could still be in your pajamas, I wouldn't know. All right, so today we're going to start Calc 3. Now, what is Calculus 3? Well, I like to explain Calc 3 as Calc 1 in 3 dimensions. Everything you ever learned in Calc 1, we will reinforce, but we will do it from a multidimensional point of view. Now, here's a simple way to consider calculus. In Calc 1, you learned limits, you learned derivatives, you learned integration, you mastered the calculus of 2 dimensions that you could do pretty cleanly and easily without any major tricks. Calc 2, you filled in the gaps and you figured out how to integrate everything that could be integrated that you didn't know in Calc 1. Then you did sequences and series, you did all of this really cool stuff. So at the end of the first 2 semesters, what you did was you mastered the calculus of 2 dimensions. And that is extremely important. Problem is, we live in 3 dimensions. And when you take physics, it's 3 dimensions. There isn't anything really in 2 dimensions. So now that you've mastered the calculus of 2 dimensions, we now have to expand and extend it to 3D and say, how do we tweak what we know? Not change, not relearn, not start over. Take what we know and expand it so it still works in 3 dimensions. And what you're going to find is some of the problems that really troubled you, maybe in Calc 1 and 2, that you thought were really, really difficult, when we do it from a 3-dimensional point of view, sometimes it actually makes it much, much easier. And that's kind of a cool thing. So we start this course. The first few weeks, we're going to do vector analysis, the algebra of vectors, and in some cases, the calculus of vectors. There's something called vector calculus. That's what we do at the very end of the course that's completely unrelated to what we're doing now. Now we're doing essentially the calculus of vectors, which is a much lower level thing. Those who have had Physics 195, you have a lot of exposure to vectors. The difference is in Physics 195, you were told, here's the vector, use it, answer the question, don't ask why. In other words, you have no idea what you did or why you did it. You just knew that was the right thing to do, but without really the foundational grasp. This is the class that sets the foundational grasp for everything vector. We explain where everything comes from, and we primarily will focus in this class on vectors in 3 dimensions, but understand vectors are actually multidimensional. For those who have had linear algebra or are in linear algebra, we study vectors intensely, but not in 3D. No, we study them in n dimensions. In other words, all dimensions. We're not limited to 3D, but in Calc 3, we have no reason to go beyond 3D. So we'll keep it simple. So what is a vector? Well, a vector in the simplest sense, and by the way, the drawings that I do when I'm doing it in class, primarily I'll do things in 2 dimensions because sometimes it's very difficult to interpret a 3-dimensional drawing. I will do 3-dimensional occasionally, but right now, if I said, what is a vector? First of all, a vector is a directed line segment. And when I say directed, I mean it has to have a starting point and has to have an ending point. The nice thing is the starting point is always the origin, and the terminal point, let's say that terminal point is the point A comma B, that point on the XY plane. Then what I do is I describe the vector using the terminal point. So if this is vector V, we'll call V vector V, the standard notation when you're printing it is you put a little hat on the V. In print, the difference is a vector will be a bold V. So you're reading something and you see this really bold symbol, you know that means a vector. When we print it, we don't usually write the hat. But if I'm drawing it on the board, I'm not gonna, let me make my V really bold. Well, no, that's just impractical doing it that way. So I put a hat on it. Now there's something special about the hat because there's a notation thing going on here. So I call this vector V, and then we use these sort of triangular brackets, A comma B. This refers to the vector whose terminal point is the point AB. So this picture. Now, a vector is not a numerical value. A vector is a thing, okay? A vector is a thing. It has length. It has direction. Because I could take a vector of this length and point it in any direction around the circle, okay? The length wouldn't change, but the vector would be different because it'd have a different terminal point. Now, the notation, I want to go really quickly because most of you probably are somewhat familiar with your high school geometry, okay? In high school geometry, you talk about lines, you talk about other things. Let me give you some simple things here, because I want to make sure we understand the differences in notation. This is a line. The arrows indicate it goes both ways forever, and we generally write it this way. AB with that picture on top. This is a ray. A ray is infinite, but it has a beginning point and then goes in one direction forever. And it's generally indicated this way. This is a line segment. It has a beginning and an end, but it's non-directional. It doesn't matter which way I'm looking at it. I'm looking at the whole thing. And we generally write it this way. So the notation indicates what it is. Where it can get confusing in the vector sense is vector notation looks a lot like the notation for a ray. It isn't, but there are similarities. A ray has a beginning and it goes in one particular direction. So the second symbol tells me it's passing through the point B. The difference is the ray is forever. The vector is terminal. The AB, it doesn't start at A, it ends at B, it ends at the ordered pair AB. So sometimes there's confusion from a notation standpoint. This is high school geometry. You guys remember this. We don't use this notation in this context because it can get too confusing. So when we're talking about vectors and we're talking about lines in the same context, we'll make it very clear, and we're going to use notation where there's just no possible way you can get confused, okay? So with that said, one of the first things I can ask about a vector is, how long is this vector? How long is this vector? Well, this vector goes from here to here. Well, if I make a little right triangle here, then this side of the right triangle would be A and this side would be B. So I know simple Pythagorean theorem would tell me the length of this vector. So how do I describe the length of a vector? Now remember, a vector is a thing, okay? A vector itself isn't a number. So if I want the length of the vector, I have to figure out a way of asking that. Now, we have similar notation. In geometry, we have ways of asking questions. Again, I taught high school geometry for many years, way back when. If I was talking about an angle, this is geometry. I'm talking about an angle, and let's just call it angle 1, for lack of a better name. Now, an angle is a thing. An angle doesn't have a value. But if I got out my protractor and I said, well, what is the measure of that angle? Whether it be degrees or radians, what is the measure of that angle? What numerical value describes that angle? I don't say the angle equals a number. I would say the measure of angle 1 equals, let's say, 45 degrees. Angle 1 is the thing. So it'd be kind of like me saying, Bob here equals 150 pounds. No, Bob is a person. Bob is not a number. Oh, but if I want to take a measurement of Bob's weight, the measurement of Bob's weight equals 150 pounds. That makes sense. Bob, the person, doesn't equal a value. A measurement of Bob would equal a value. So the measurement of the angle. If I was talking about the line segment from A to B, and I wanted the measurement of the line segment from A to B, well, there were two ways to do it. In high school geometry, you put a little m, or you just said AB without the bar, and that would be a numerical value. Okay, so when I have a thing and I want a measurement of the thing, in geometry, if I gave you a rectangle and I wanted the area, I would just say the area of the rectangle is. So I want the length of this vector. So how do I say that from a notation standpoint? It's actually quite simple. There's a symbol that's universal, and this is used in many different contexts, and it always means the same thing. It's the double bar. Now, in Calculus 1, you saw this, right? That was called the norm of the partition. That's part of the fundamental theorem of calculus when you're writing down the Riemann sum. Does anybody know what double bar means literally? Whenever you see that, there's one word.
Magnitude.
Perfect. A lot of people make the mistake of saying length. Length is a form of magnitude, but it means magnitude. Now understand, magnitude is whatever you're measuring. But magnitude isn't always a length. If you've had physics 195, the magnitude of a vector might be force units. Oh, the magnitude of my vector is this many newtons or this many pounds. The magnitude of a vector could refer to an area, or I should say magnitude in general, not just magnitude of a vector. The magnitude of a vector usually has units associated with it. So rather than saying simply the length, we have to be careful, because in our class, we're going to do multiple integration. So magnitude will sometimes be length, sometimes it'll be area, sometimes it'll be volume. But magnitude just means the measurement of what I'm doing. So the magnitude of this vector would be simply a squared plus b squared under the root. And we use a double bar. There's another symbol that we sometimes use that's similar to a double bar, and that's a single bar. What does single bar around a value generally mean? Anybody? If I put a single bar around a value, like, you know, if I said, yeah, and by the way, a lot of textbooks really mess this one up badly. Absolute value and magnitude are not the same thing, and they do not have the same definition. And here's the simplest way to think about it. There's no such thing as the absolute value of a thing. You can only take the absolute value of a numerical value. I can't take the absolute value of Bob. Okay, that doesn't have any meaning, but I can find the weight of Bob or the height of Bob or the age of Bob. I can do measurements of Bob. Bob doesn't have an absolute value. A vector does not have an absolute value. And many textbooks use absolute value and magnitude interchangeably. They are not. Here's the simplest reason. First of all, a thing, you can't take an absolute value, and magnitude always has units. Absolute value never has units. Okay, you would never say the absolute value is some number of centimeters or some number of newtons or some number of something. No, but a magnitude will have units. So we never use absolute value in a vector sense. But having said that, there are many textbooks who do, because the authors are just, well, they're kind of lazy and they don't make the distinction. You want to be careful in that regard. This is a very simple notion. So right off the bat, how does this help me? Well, I said before, a vector has actually two things that always describe it. One is its magnitude. So when I'm visually looking at it, yes, that's how long it would be. Secondly is the direction it's going. So the direction it's going, in this case, if I put an angle here of theta, you'd say my vector v is this long in this direction. And that's a really simple thing in 2 dimensions. But what if I'm in 3? Then the angle is a little more confusing. There's some little more going on here. So let's talk about what we can actually do with vectors. Okay, so the most important mathematical property that anything can have when you're talking about an operation, for example, we're going to talk about addition in a moment, and then we're going to talk about other things. The most important requirement whenever you're talking about an operation is the concept of closure. Now, those who've had linear algebra understand closure. It's the same closure. For a set to be closed relative to an operation, in really simple English, means if I take 2 things from the same set and I add them together, that result will still be in that set. That would mean that set is closed to addition, or it's satisfying closure of addition. Now, is that an automatic thing in mathematics? No. Actually, closure is extremely difficult to attain. So I'm going to give you some really simple examples, and I'm going to start with something that everyone's familiar with. I do this in my remedial algebra classes. Now, the number groups that we know of. If I said the numbers 1, 2, 3, 4, 5 forever and ever and ever, we usually call those the counting numbers or the natural numbers. We're familiar with that. If I throw in the 0, then I have what are called the whole numbers. If I consider every positive and negative whole number, that's the set of integers. Now, depending on your level of math, up till now, you always used a capital I. Does anybody know what the symbol for integers is pretty much from this time on? If you've had discrete math or linear algebra, what symbol do we use for integers? We don't use an I anymore. Anybody know? Yep, good. We use a Z. Now, here's the way I think about it. When I'm working with a math student and they use a Z for integers, I say, aha, they know. They now know the secret handshake. They know the backdoor in. I don't know why we changed the symbol around Calc 3, but you never use an I for integers ever again. You always use a capital Z. I wasn't there when they decided, but that's what we do. Now, if I take every conceivable quotient of integers, that is the definition of a fraction, or A rational number. Q is the set of rational numbers. It's every number that can be written as a quotient of integers. Well, the number 5, can that be written as a quotient of integers? Yeah, 5 over 1, 10 over 2, 15 over 3. So we know that integers are rational. Now, every integer can be written as a quotient of, every rational number can be written as a quotient of integers, but rational numbers also have a decimal form. The decimal form of a rational number. If I said 1/2, I know that's 0.5. If I said 1/3, I know that's 0.333 forever, never, never, which we usually would just say. A rational number takes two different possibilities. A rational number either has a terminating decimal or it has an infinite decimal where there's a repeating pattern. It doesn't have to be the same number over and over again, but it has a repeating pattern forever and ever and ever. That's the definition of a rational number. So the definition of an irrational number, well, if the decimal terminates, it's automatically rational. So an irrational number must have an infinite decimal that never repeats. Pi, square root of 2, e. These have infinite decimals that never repeat. So if I put these two together, the rationals and the irrationals, now I have every considerable decimal way of writing a number. I put the two together, I get the real numbers. Okay, that's the set of real numbers. They're either rational or irrational. Now, later in this course, okay, and in linear algebra, we sometimes consider, what about the imaginary numbers and the complex numbers? Yes, that is a whole nother thing, but not for this course. We are going to stay away from them for the most part. In linear algebra, we study them, but near the end of the course. And then when you get to differential equations, everything's complex, and but not for this course. So these are considered the basic number groups. Are they all closed? Well, we'll keep it simple. If you were taking discrete math, Math 245, one of the most basic proofs we do is you prove some of these sets are closed. For example, you formally prove that if you add two rational numbers together, you get back a rational number. If I add two natural numbers, two counting numbers, am I always going to get back a counting number? Yes, I am. Whole numbers? Yes, I am. If I add two integers, will I always get back an integer? Yes, I will. Now, there are infinitely more irrationals than there are rationals. In fact, if I take any two rational numbers, this is kind of a crazy one. If I take any two rational numbers, no matter how close together they are, 0 and 0.000001. There's an infinite number of irrational numbers between any two rational numbers. There's way more irrationals than there are rationals. If I take two rationals and add them together, I will always get back a rational number. And if I take two real numbers and add them together, I'll always get back a real number. You don't have to prove some of these. I'm going to take two irrationals and add them together. √2 plus pi. Well, I know that's irrational. That's not even a question. So clearly the irrationals are closed, right? Because if I take negative √2 and I add it to √2, then I'll get 0. But 0 is rational. Oh, I just proved the set of irrationals is not closed. In fact, this is it. This, that's it. Unless I'm considering complex numbers, of the infinitely many sets of numbers you could come up with, those are the only ones that are closed. Closure is a really difficult thing. In fact, if I said, okay, let me just make a really small number group. I want 1, 2, and 3. Well, obviously, if I add any two of these numbers together, I'm going to get back something in that set, right? When I add 1 to 1, I get back 2. When I add 1 to 2, I get back 3. And when I add 2 to 3, 5's not in the group. In fact, finite sets of numbers are not closed. There's exactly one finite set of numbers that is closed to addition. Does anybody want to guess what that set looks like? There's exactly one set of finite numbers that exists that's closed to addition. It's not very exciting. It's that one. That's the only set of numbers that's finite that's closed to addition. Closure is unbelievably difficult. So why am I going over it? Because the most important vector property is the fact that vectors are closed to addition. So I'm going to show you and I'm going to prove it. And this is kind of huge. So there's some notation that I want to introduce that you're going to get very comfortable with over time. The set of real numbers, we generally use a script R. The XY plane. If I'm talking about the XY plane, we use this notation. And we actually say R2. We don't say r squared, we say r2. If you've had discrete math, it's the Cartesian product. It's called the Cartesian product of r cross r. That's where it's the real numbers in one direction, real numbers in another direction. XYZ space is called R3. So whenever you hear someone say R3, they're talking about 3 dimensions, 3 space. But the nice thing is I can talk about R4, R5, R12, R100. When I'm talking about coordinates, then coordinates in R2 look like this. Coordinates in R3 look like this. And in fact, in general, we'd say coordinates in Rn, I'm going to write like this. This is an element of R2. This is an element of R3. I have n of them, so now we usually just write it this way. This would be an element of Rn. This is notation. That just means n dimensions. Can I have more than 3 dimensions? Yeah. The number of variables is how many dimensions you have. Right now I have 2 variables. Right now I have 3. Right now I have n. You've dealt with higher dimensions all your life. The tricky thing is a lot of you are thinking about what does the picture look like? How do I graph multi-dimensions? Don't worry about graphing things. You can't graph anything bigger than 2 dimensions. Right? I can draw a picture of something in 3D, but I can't physically represent 3 dimensions on a 2-dimensional board. I can draw a picture of a cube. I can draw a picture of a sphere, but it's still a 2-dimensional rendering of a 3-dimensional shape. I can't draw something in 4 or 5, 6 dimensions, but it makes perfect sense to talk about higher dimensions. Again, the number of variables. So in the XY plane, we generally consider 1 independent variable, 1 dependent variable, right? 1 input, 1 output. That produces an ordered pair. In 3D, we're going to have X and Y be the input eventually, and then Z be the output. No big deal. So can I have a whole bunch of inputs and 1 output? Yes. That's a very, very common thing that we're going to do. And I'm going to give you lots of examples later on of that. So a vector, vectors live, we're going to start with a vector in Rn. I'm going to give you the general before we do the specific. So let's consider vector u and vector v are elements of Rn. That means they're both n-dimensional. That means vector u looks like this. u1, u2, dot, 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 un. Vector v is v1, v2, vn. I said before, most of this class we're going to be dealing in 3 dimensions, but sometimes the rules we want to state in general, because what I'm going to show you is true in all dimensions. You don't have to prove it 1 dimension at a time. So now we're going to do a definition. U plus V. We're going to define this. Now, some of you may or may not be familiar with the next symbol. 3 bars. 3 bars is the symbol that means is defined as. It's not an equals. In fact, it's far more powerful than an equal sign. If I said 3 plus 4, well, that equals 7. Equals means I'm coming up with a result. But a definition, if you looked up a word in the dictionary, you looked up that definition, you can't question the definition. That's what it is. But if I said to you 3 plus 4 equals 17, you could question that and say, no, no, I can show that's not true. A definition is an absolute. It's an unquestioned statement. You have actually learned this symbol in multiple places in your lifetime, and I'm going to give you a simple example of that. So a simple example would be, you have a unit circle. This is the easiest one to remember. On the unit circle, right, circle of radius 1, X is defined to be the cosine of theta. Y is defined to be the sine of theta. All of trigonometry is based on this definition right here. You can't calculate the cosine of theta. You can't calculate the sine of theta. Cosine of theta is defined to be the X value. The sine of theta is defined to be the Y value. And that's why using Pythagorean theorem, since X squared plus Y squared would equal 1, that's why cos squared plus sine squared equals 1. Oh, by the way, while we're at it, y over x is defined to be the tangent of theta. But isn't that equal then to sine theta over cos theta, based on the previous definition? this is the definition. This is a result of the definition. Equal signs are results of definitions, but definitions are what they are. I'm going to define what it means to add two things. After that, every time we use it, it's a result. So you can just put an equal sign. The definition of vector addition is that I add corresponding components in their position. Sorry, get a little bit tight here. In the regular classroom, I have 50 feet of board to work with. So I add these two, comma, all the way down the line. Okay, this is the definition of vector addition. But if the u's and the v's, the u1s and the v1s are simply real numbers, then u1 plus v1 is just real number addition. But I know something about real number addition. Isn't this quantity equal to v1 plus u1, v2 plus u2, vn plus un? Isn't that automatically true? Because this is real number addition. And what did I just use? Real number addition is what? What property is that? Anybody? Yell it out if you know it.
Cumulative?
Commutative.
Oh, yeah.
Real number addition is commutative, and these are real numbers. I'm just looking at the real number within the vector. But if real number addition is commutative, then this result is equal to this result. But that would mean that this result is equal to v plus u, isn't it? Because based on my definition of vector addition, wouldn't this be v plus u? Oh, well, this is kind of convenient. Our definition of vector addition leads to the result that vector addition is commutative. Oh, that's kind of cool. Vector addition is commutative. But isn't everything commutative? No, actually most things aren't. No, most things aren't commutative. Is subtraction commutative? Is a minus b equal to b minus a? No. Is exponentiation commutative? Is a raised to the b power equal to b raised to the a power? No, it's pretty much not true. Is a over b equal to b over a? Division commutative? No. Anybody who's done matrix multiplication? Is matrix multiplication commutative? Matrix A times matrix B, is that equal to matrix B times? No. No, actually, very, very few things in mathematics are commutative. But whenever I can show addition's commutative, that's huge. So if I was doing this with simple numbers, let's use simple numbers. So I've got vector u is 2, 4, -1, 3. Vector v is -6, 4, 3, 0. Now notice, first of all, both vectors are in the same dimension. The first rule of vector addition is your vectors have to be in the same dimension. Okay, I cannot add a 2-dimensional vector to a 4-dimensional vector. There's no meaning. So vectors have to be the same dimension. Vector addition is closed. If I add two vectors of the same dimension, I will always get back a vector in that dimension because the definition of vector addition, right? The definition, by the way, let me put this out there. I took two vectors in Rn, and when I added them together, I got back a vector in Rn. That is huge. That's astronomically important. It's simple, but it's important. So I'm taking two vectors in R4, okay? So if I'm gonna add these two together, 2 plus -6, 4 plus 4, -1 plus 3, 3 plus 0. It's that simple. Vector addition is very, very simple. And notice I got back a vector in the same dimension that the original ones are in. That's important. So vector addition, piece of cake, right? Nothing about that is in any way tricky or confusing. Now, I'm going to give you a simple visual that might help. Now, most of you have probably seen this in some capacity, but being in Calc 3 means you probably haven't done any vector algebra in a very long time. Most of you, it was probably trigonometry the last time you really did vector algebra. So on the XY plane, keep it real simple. All right. I have vector u. I have vector v. What does it mean to add u and v? Well, if I said u and I want to add v to u, what I'm literally doing is taking vector v, picking it up and attaching it to the end of vector u. I'm taking that vector and I'm just doing this. And what is my result? Well, it'd be this new vector right here. Now, this new vector would be u plus v. But what if I take vector v and I want to add vector u? So then I'm going to take this vector and add it to the end of here. So if I took v and added it to the end of u, I get this. If I take u and add it to the end of v, I got this. But in either case, you notice our result is that vector there. We got that vector there regardless of what order I added them. By the way, the outer shape, does anybody know what that shape actually is? Don't go by the accuracy of my drawing. If I took this one and added it to here, or I take this one.
Parallelogram?
The parallelogram. And two vectors will always uniquely determine a parallelogram. And by the way, that becomes really, really important. We're going to use that in our next lecture on Wednesday. But I get a parallelogram by putting those together. And so the sum is just the diagonal of the parallelogram that those two vectors uniquely determine. So that's kind of cool. Now, I'm giving you a two-dimensional picture, but this would be true in every dimension. That I have two vectors out in space and they're, I just add one to the other. Most of you, if you think back to like trig, when you talked about vectors, the kind of stuff you would do is something like this. You have an airplane that is going due north 500 miles an hour. And there's a 50-mile-an-hour wind blowing due east. Do you guys remember doing stuff like that? So what is the plane actually doing? And what you did was you took the 500-mile-an-hour vector and you added the 50-mile-an-hour vector, and then you say, well, the plane's actually doing this. And you'd be correct. You'd be adding the two vectors, and the result is where the plane is actually flying. It's a very simple example, but it's actually quite accurate and quite useful. Now, the only other operation we can do with vectors, we've got vector addition. Now we're going to define something called scalar multiplication. Okay. A scalar is simply a number, a numerical value. You can think of it as a constant, if you will. Scalars can be variables, but a scalar is a multiplier to something. So I could be multiplying a vector. I could be multiplying a matrix. I could be multiplying a polynomial. The thing I'm multiplying by is called the scalar, okay? The term scalar actually comes from a completely different context, okay? I personally use Google Maps a lot. I don't do the phone thing. I'm that person who actually, when I'm going to go somewhere that I don't know, I go to Google Maps, I look it up online, I look at the directions, and yes, I will actually print the directions out, right? So I'm looking at that. But when I'm looking at that map, and I'm looking, wow, from here to LA is only 2 inches. No, it's probably more than 2 inches. So then in the corner, you'll have some sort of a legend. That's the thing. It might say 1 inch equals 50 miles or something like that, okay? That's because a map is always a scaled down version, okay, of the actual. But I could take something small and then blow it up and make it huge like a statue. Then I'd be scaling up. The multiplier that we would multiply by to make it bigger or to make it smaller is called the scalar. That's where the term comes from. It originally comes from maps, but anytime you're doing something, New Year's Day parades, right? Thanksgiving, the floats, the giant pictures, giant turkey that's 300 feet, that's a scaled up version of it. You've multiplied by a scalar. That's literally what the word means. So scalar multiplication on a vector means I'm going to take a vector of a particular length and I'm going to make it either longer or shorter by a constant multiple. So if this is, let's say the blue one is vector v, then we'll say the orange one is k times vector v, where k is a real number. We'll say it like that. K is an element of the real numbers. If k was equal to 1, then my scaled vector would be identical. What if k were equal to 0? Then I would have a vector of length 0, which is actually possible. Okay. What if k were negative? Anybody want to try that one? What if k was a negative number?
Would flip the vector?
Yeah, point in the opposite direction, exactly. It wouldn't change, wouldn't go in some weird direction. If k were 2, then this is twice as long. But if k were -2, then it's twice as long in the opposite direction. So a scalar just multiplies. That's it. That's the physical effect of a scalar. So what about in terms of what it looks like on the vector itself? So if we define k times, I'll use my previous vector v. Okay, we'll call this kv. When I multiply a vector by a scalar, then I'm multiplying each individual element by that scalar. Okay, it goes into every single one of them. Okay, fairly simple notion. So, okay, that's it. That's scalar multiplication. Where is this used primarily? All right, so here's the deal. I'll use Shreyas as an example because I know Shreyas is here. So Shreyas, I need you to go, you can't tell, I'm going to point 7. I need you to go that way. By the way, and I'm giving you a very specific direction. I want you to go that way. By the way, how far is that way?
No idea.
So in other words, that way technically could be infinite, couldn't it? I just said go that way. Oh, I want you to go that way 100 feet. That's different than saying go that way 100 miles. So that way you could start drawing a line in my direction, but that line is infinite. I don't want you to walk forever. I want you to go 100 feet. I want you to go 10 feet. I want you to go 1,000 feet. How can I pull that off? Here's the easiest way to do it, okay? And I'll draw a picture in 2 dimensions. Here's a vector. It's not even important how long that vector is. That vector, for all practical purposes, could be infinitely long. It could be, 1 atom long, but there's a clear direction there. I want you to go in this direction 100 feet, or in this direction 1 foot, or in this direction 10 feet. How do I do that? The easiest way to do that, this is vector v. Vector v has a certain magnitude, okay? What I want to do is take the reciprocal of the magnitude and multiply it by vector v. Now think about this for a moment. If I had a vector that was 100 feet long, and I now multiplied that vector by 1 over 100, wouldn't my resulting vector be exactly 1 foot long? I have a vector that's 1,000,000 miles long, and I multiply by 1 over 1,000,000 miles, I'm going to get a vector that's 1 unit long. If I take a vector regardless of its length, and I multiply it by the reciprocal of its magnitude, this is a scalar. This is unitless, remember. This is right now, I'm just saying this whole quantity would be of length 1. This is called a unit vector. Unit vectors are very important. So the unit vector, let's say, is that one right there. This vector right now has length 1. It's 1 unit from the origin. Regardless of how long this one was, I've now created a vector of length 1. I said I wanted Shreyas to walk 100 feet in that direction. So what would I do? I'd take this vector and I would multiply it by 100. It doesn't matter how long my original vector is. I take my original vector, I make it of length 1, and then I multiply that vector by any number I want. So anytime you have a situation where I say, I want you to drive in a particular direction, and here's how far I want you to drive. I want you to get in your car and drive due east, exactly 1 mile. Well, east technically is forever. So take east and make it 1 unit long, and now multiply your 1 unit by 1 mile. So a unit vector is extremely useful. So I make things in the unit vectors and then I multiply them by the appropriate length. That's a very, very common move. That's one of the reasons that the magnitude is so important to understand. Okay, so this is scalar multiplication. Now I want to go over a couple of the algebraic steps of vectors. They're also very, very important. Now, algebra, if I talked about, and I mean low-level algebra, not higher-level algebra. Algebra only gets more abstract as you go higher than this class. In lower-level algebra, you solved equations, simple equations. Maybe they were linear equations, maybe they were quadratics. You did things, you isolated the variable, you added things to both sides. You did all sorts of stuff. The question is, what justified the things you did? And sometimes we forget. If I said, for example, I want to solve, I'm going to start really simple. I want to solve the problem x minus 5 equals 7. I want to solve this problem. And you're in lower level algebra. Well, you know what to do. You didn't have to think about it. But if you're explaining to someone what is valid, what's legal, what's not legal, because I might have variables on both sides, you'd say, well, I do know one thing about equal signs. If I add the same quantity to both sides of an equal signs, I will have preserved my result, regardless of what I get. So just for fun, if I decide to add 37 to both sides, for no good reason, if I decided to add 37 to both sides, whatever I write will have the same result as this will, because I have not changed anything. But if I said, I want you to add 37, but only to one side, well, then I've completely changed the problem. I will not have preserved the solution. So what we do is we use the addition property of equality, which says if I add the same quantity to both sides, that's number one. Second, I'd say, well, what quantity do I want to add? Well, let's see. I'm adding -5, so I would choose to add the additive inverse of -5, which would be +5. Okay, now, when I add my +5, by the way, does it matter which side I add it? No, that's commutativity. It doesn't matter which side. But when I do this, I need to regroup these. That's associativity. When I take my -5 and I add it to my 5, I get the additive identity, which is 0. And when I take something and I add it to the additive identity, I get the same thing back again. I know my result is 12, but there were actually 5 completely separate, unrelated steps that had to be done that validate this. We generally do one step in our head. But if someone says, how do I know that what I did was valid? You'd say, well, I used the addition property of equality. I used additive identity, additive inverse, commutativity, and associativity. And that was just that problem. Turns out there are 11 properties of algebra that we are aware of. The same 5 hold true for multiplication. The multiplication property of equality, right? If I multiply the same non-zero value on each side of the equation, I preserve the result. Inverse identity, commutativity, associativity. And there's one more property, an 11th property, the one that combines addition and multiplication. That would be the distributive property. There are 11 properties of algebra that we use every time we solve a problem that justifies what we did. But that's real numbers. How many of those properties would apply if I was dealing with vectors and not numbers? Well, it turns out most of them, which is really kind of cool. Remember, the properties of algebra only apply to addition and multiplication. Not one of them applies to subtraction. Not one of them applies to division. Those don't have any operations, only addition and multiplication. So, for example, I have 2 vectors, and let's say they're in Rn. It doesn't really matter. In fact, I'll make it easy. I'll say they're in R2. I'll keep it simple. So vector U is U1, U2. Vector V is V1, V2. All right? I would like to know, is there a vector out there? Oops. Is there a vector out there that when I do U plus V, that I just get back U? Is that even possible? Well, let's see. Well, what's U plus V? U plus V I know is U1 plus V1, comma, U2 plus V2. And I want that to be simply U1, U1, comma, U2. Well, how the heck could that be? How could U1 plus V1 simply equal U1 and U2 plus V2 simply equal U2? Is that mathematically even possible? It is when? If V1 is 0 and V2 is 0. Oh, so is there a vector V out there where this result is true? Yes, we just figured it out. What would vector V have to look like? It would have to look like this. We have a very clever name for this vector of zeros. You'd never figure out what this is called. It's deep and hidden and probably in a strange language. Does anybody know what we call this?
The zero vector.
Oh, yeah. You read ahead. Yeah, we just call it the zero vector. Now, the problem with the zero vector in general is the term zero vector does not refer to what dimension you're in. But You're never going to be working with multiple dimensions at the same time when you're doing vector stuff in this class. In other words, the entire problem we're in 2 dimensions. The entire problem we're in 3 dimensions. You can't be working in 3 dimensions and have a 2-dimensional zero vector. That doesn't have any meaning. So you don't usually have to worry too much about defining your dimension, but we call it the zero vector. And we have a very clever name for it. We write it like this. We put a 0 with a bar over it. Now, in higher level classes where you actually are working with multiple dimensions, you would often do this. I'm going to put a little subscript of 2 to refer to this being 2 dimensions. That's good form, but in this class, it's not really necessary. You can just write it like that. Now, never confuse the zero vector with the scalar 0. They're completely unrelated things. The zero vector technically is the origin. The number 0 is a scalar that's 0. They're not the same thing. Quite different animals. So we have a vector that acts like an additive identity. There is an additive identity of vectors. Now, with that said, new problem. I have a u and a v in R2, and I'd like to know, I want u plus v to equal the zero vector. I would like to know, does a vector have an additive inverse? Does it have another vector that when added produces the additive identity? Well, that would mean, again, that u1 plus v1 is 0, and that u2 plus v2 is 0. But that can only be true if v1 equals the negative of u1, and v2 is the negative of u2. So that means in this context, my v must be negative u1 comma negative u2, or simply the negative of vector u. So there is an additive inverse of a vector. It's a vector with a -1 in front of it. It's a pretty simple notion. So that's really kind of cool. Now, vector addition is commutative, it's associative. Addition isn't distributive. I can distribute a scalar into a sum. So vectors have a lot of the same properties. There's closure, right? If I add any 2 vectors of the same dimension, my result is a vector of that same dimension. So vectors have a lot of properties that numbers have, and that's really a cool thing. It's a very powerful thing. So what's one of the things we do with vectors? Well, one of the things algebraically we do, and again, it's a simple exercise. Let's start with something simple in 3D. Let's say vector u is 4, -1, 3. Vector v is 6, 5, -4. I would like to find 3 times vector u minus 4 times vector v. This is what is called a linear combination. That's a term you hear a lot when you're working with vectors. A linear combination. The combination means I'm going to combine more than one. Linear means I'm only using scalar multiples, right? Well, when it comes to vectors, you can't square a vector. You can't have the cosine of a vector. So a linear combination just simply means you're adding scalar multiples of the things. So if I add the scalar multiples, my result should be a vector, in this case, still in R3. So the easiest way to do this problem, see, the thing is, I don't want to be just right. I want to be right efficiently, and I want to be right absolutely. I don't want to question it. A lot of times we make silly mistakes because we try to do too many things in our head or just work too fast. This is a simple problem, yet if I ask this problem on a quiz, I will get a lot of incorrect results because people will work too fast and aren't really looking at the big picture. So let's start by taking 3 times vector u. What is that? So that would be 12, -3, 9. And do not subtract 4 times vector v. I guarantee you, if you subtract 4 times vector v, 2 of your 3 numbers will be wrong. They're always wrong. You never want to do distributing with negatives because you mess it up. No, add. I'm telling you from experience, when people subtract, they make mistakes. No, add -4 times v. So -4 times this would be -24. -20, +16, and then my result would be what? -12, -23, 25. That's it. It's a linear combination. Piece of cake. Not a whole lot of questions I can do here because we're just looking at literally arithmetic of vectors. This is not complicated stuff, but it's the starting point. Now, next day, oh my goodness, Next day is huge. Next day we define and show dot product and cross product, which are two humongous vector operations that we're going to define. And again, if you have vector experience, particularly physics, you're probably well versed in these, but you may not know the why. You might be able to do things, but if you don't know the why, then it's hard to extend it in other areas. And when you get to linear algebra and other classes, you go way, way beyond what we're doing here. Now, this is the vector stuff here. So now I'm going to look at something a little bit different using some of the vector resources that we have. And one of the things we're going to see later is that the ability to change things into a vector form to make our life easier, which sounds really strange that I would want to change something that's not vectorish into a vector form to make things easier. Yeah. Now, I want you to consider the following, okay? I know the Pythagorean theorem. I'm not asking you to prove the Pythagorean theorem. I know the Pythagorean theorem. Let's suppose this is a rectangle. This is side A, this is side B, and I would like that length. Let's call that diagonal for D. I know that this is a simple Pythagorean theorem. I know that D squared equals A squared plus B squared. I have no doubt about that. That's a piece of cake. Now I want you to, whatever room you are in, I'm assuming your walls are flat and straight and you're not in a dome or something. I want you to look at one corner of the room, and then I want you to look at a different corner across the room ceiling. So I want you to consider the following. Oops, let me erase that part here. I don't need this anymore. I want to consider now, this is not a rectangular prism. This is a picture of a rectangular prism. It's still two-dimensional. What I'd like to do, I would like to find the distance from that corner to that corner. And that's still a diagonal, but that's a diagonal in 3 dimensions. Oh, so how does that work? This is a little bit trickier, isn't it? So let's suppose, let's call this length A, let's call this length B, let's call this length C. Then we'll call this length D, D for diagonal. I would like to determine how to figure this out. Darn, if only I could use my Pythagorean theorem, but it's 3-dimensional. I've got too many sides. Do I have any right angles anywhere? Yeah, it turns I do. So you consider. Okay, I think we all agree there is a triangle there. Is there a right angle anywhere in there? And again, you're looking at the picture. So again, I want you to think of the room you're in, go from corner to corner on the opposite side, and imagine, or just take out your marker pen and draw on your walls if your roommates or your parents don't get upset. Okay, maybe that's a bad idea. But do I have any right angles? Yeah, I do. I have exactly one. It's right there. I have a right angle because these planes are at right angles. So if I look at my walls or I look at my ceiling in a wall and I say what angle is made if I draw, I'm always going to have right angles there. I don't have right angles going down the diagonal, but I definitely have a right angle right here. So that means that this is the hypotenuse of some right triangle. So this length here I know is C. What is this length here? Oh, but there's a Pythagorean thing going on right here. So isn't that length there the square root of A squared plus B squared? That length right there is the square root of A squared plus B squared. That length is C. So can I accurately say that D squared equals the square of this side plus the square of this side? I can say that because this triangle is 2-dimensional, even though it's sitting in a 3-dimensional picture, which means that my diagonal is A squared plus B squared plus. Oh, folks, do you realize we've just derived the 3-dimensional Pythagorean theorem? That's the thing. The Pythagorean theorem is very useful. but it only lives in 2 dimensions. Don't you have to find distances in higher dimensions sometimes? Yeah. We just found the length of this diagonal. The square of that was the sum of the squares of all of these. Now, this is actually an extremely important result. And I'll tell you why this is so important. Yeah, 3-dimensional Pythagorean theorem. Very, very cool. All right. Vector V is, keep it simple, V1, V2, V3. I would like the magnitude of vector V. We did it in 2 dimensions and it was simple Pythagorean theorem, but how do we do it in 3? How about if it was in 4 dimensions? Sum of the squares. How about if it's in 27 dimensions? Sum of the squares. Doesn't matter what dimension you're in. It's still Pythagorean theorem in a higher dimension. So that's why that result is so important. If I'm finding the magnitude of a vector in a higher dimension, it's still the square root of the sum of the squares. That didn't change. I just proved it to you by doing it in 3D. It's the same in 4, 5, 6, 7, 8. That is very, very useful, as you can probably tell. So the magnitude of the vector is always the same thing. You take the square of each of its components, add them up, and take the square root. Does not matter what dimension you're in. Cool. So let's use that in a geometric way. Okay. I'm going to remind you of something you already know. Keep it simple. All right. I have a circle. Very simple. And let's say the radius is r, and that's the point x comma y. Well, I know, using Pythagorean theorem, I know that x squared plus y squared equals r squared. We know this. And we know this is the equation of the circle centered at the origin of radius r. We know that. That's old stuff. But sometimes we forget why. Well, really what we have is the distance formula going on. The distance from 0, 0 to xy, remember it's x minus 0 quantity squared plus y minus 0 quantity squared. And that square root equals r, which is why when we write it, we don't write it with a square root. We'll say, well, that was simple enough. Okay, that was. So now let me change it a little bit to something that we're also very familiar with. Okay, I have a circle of radius r and I just moved it. This is what's called a translation. I just moved it, so now the center is no longer the origin, the center is hk. So what's this equation? Oh, shoot, that's totally unrelated, isn't it? No, it's the same thing. Distance formula, or you can just go like this. Isn't that x minus h? And isn't that y minus k? So the equation of this circle is x minus h quantity squared plus y minus k quantity squared equals r squared. And again, we know this. This is remedial algebra. Now, if I was back at the origin, h and k would both be 0, and I'd be back to where I was. Great. So why am I showing you all this? Are we doing circles in this class? No, we're never going to do circles in here. No, we do 3D. So we don't do that problem. Oh, a little shade in there. See, this is a picture of a sphere. This is a picture of a sphere centered at the point x naught, y naught, z naught of radius rho. Usually, it's a context thing. Usually when you're dealing with circles, we use r for radius, and that gives us the implication that it is 2-dimensional. And when we do polar coordinates and all that stuff, same thing. When we're working in 3 dimensions, particularly when I have things like spheres, we often change R to the letter rho, which basically is the Greek R. It's kind of like a lazy looking P. It's a Greek R, and more often than not, textbooks will use rho for radius when it's 3-dimensional. And when you see a rho, that just kind of gives you the connotation that you're in 3D. It doesn't matter if you use a different symbol, but this is kind of the common one. So now the question is, if this point right here is x, y, z, then what is the equation of this thing? Well, much like the circle, it would be distance formula. X minus x naught quantity squared plus y minus y naught quantity squared plus z minus z naught quantity squared equals rho squared. It's very much like the equation of a circle, and using the same idea. That 3-dimensional Pythagorean theorem, it's x minus the x coordinate quantity squared, y minus the y coordinate quantity squared, z minus the z coordinate quantity squared equals the distance squared. So that is the equation of a sphere, centered at this point with this radius. And this one is very, very useful for what we're doing. Yes, knowing everything about a circle is extremely valuable, but we rarely will work with circles in this class. We will be working with spheres more often because, again, it's 3-dimensional. So let's start simple. In case you're wondering, yes, I can draw circles and spheres. I can't draw line segments, though. And I really have a hard time making right angles look like right angles, but I can draw circles and spheres. It's a strange gift. Okay, let's suppose, okay, I want to find the equation of the sphere with radius, let's say, we'll keep it simple, with radius 10 and center 6, -3, 0. Okay, based on what we just did, this should be pretty easy. X minus the x coordinate squared plus y minus the y coordinate, so that'd be y plus 3 quantity squared, plus z minus the z coordinate squared equals the radius squared. That's it. It's actually that simple. Should you multiply this out? Well, obviously I can multiply it out. Should I multiply it out? Anybody want to try that one? So if I multiplied it out, I'd have x squared plus y squared plus z squared minus 12x plus 6y. And what is it? 36, 45, and then minus 55 equals 0. Okay, this is what I would get if I multiplied it out. This is what I got. This is multiplied out. Which form is better? First, second? Anybody? Which is more useful? What do you think? Anybody?
The first one.
The first one, because I can tell what the center and the radius is. Can any of you tell what the center and the radius is of this one? No, you'd have to do work to get it. Oh, so if you have this, you'd want to leave it. You'd want to leave it in this form. Think of ellipses and hyperbolas and all the different things when I have them in the squared form. You always want to leave it in that form because it has all the information. It's perfectly correct to multiply it out. Just what's the benefit? Nah, I don't think there is any. All right, so new question. New question. Simple thing. Find the center and radius of the sphere. And let's see, what sphere did I want to use? Oh, my favorite one. X squared plus y squared plus z squared plus 8x minus, hold on a second, 8y, and leave myself a lot of room here, minus 4z equals 0. I want you to find the center and radius of this sphere here. So of course you can all just tell me just right off that. You can just look at it and know it, right? From here to here was easy. How do you go backwards? Remember? It's not a calculus trick.
You have to complete the square.
Got to complete the square. Oh, yeah. You didn't complete the square to solve quadratic equations, although you can. That wasn't the point. You usually completed the square because you had conic sections and needed to know where centers and things like that were. So completing the square is a very useful algebra tool. So let's walk ourselves through it just in case we forgot. Now, again, this is Calc 3. Your calculus skills are probably off the chart, but some of your algebra skills might be a little rusty. So if I had something like this, baby algebra, okay? If I had x plus a, and I wanted to square it, a being any number, it'd be x squared plus 2ax plus a squared. I know that, okay? So if I had, let's say, x squared plus 10x, and I wanted to complete the square, there's an order of things you did. Remember, that is twice as big as that, and those signs are always the same. So the first thing I do is not figure out what I have to add. I have to figure out what is actually being squared. So I would write this as x plus what? What would this have to be? Anybody?
5.
5. Oh, okay. So what would have to go here? I'll put a little arrow this way. This has to be 5 squared. So for me to complete the square, I would have to do this. Now, I just added 25 to this, so I would compensate by also subtracting 25. So if I was going to complete the square, x squared plus 10x is equal to this. Now, we're doing something slightly different because we're doing it in an equation form. So rather than add and subtract, I can just simply add the same number to both sides of the equation. That's actually a little bit simpler. But a lot of you remember doing stuff like this. So going back to the top, the first thing I would do is rearrange this and group the similar variables. So the first thing I would do is write x squared plus 8x plus blank plus y squared minus 8y plus blank equals, or excuse me, not equals, plus z squared minus 4z plus blank. And that all equals 0 plus blank plus blank plus blank. That looks really terrible. Let me improve upon that. That equals 0 plus, there we go. Now, why am I doing that? Because whatever number I add here to complete the square, I've got to add it to the other side of the equal sign. Otherwise, I'm violating, right, the addition property of equality, which says whatever you add to one side, you got to add to the other, or you will not preserve the equation. So what's going to go here? X plus what being squared?
4.
It's going to be a 4. So what goes here is a 16. 16. Next, I'll use my visual aids here. Y minus, again, probably 4. So here again, I have 16 plus z minus what?
2.
2. And I'll put that, so that's going to be a 4. So this, and that is all equal to 16 plus 16 plus 4 is 36. Now, the only thing I can do now is just check my arithmetic, right? If I square everything out, is it going to work? I think it's okay. I think we did it. I think we did a bang up job. This is not supposed to be hard, but this is a very useful algebraic skill that you guys learned a million years ago. Probably haven't done it a whole lot of times recently. Now, I've rewritten this sphere into a form that has all the information I need. So now I can answer the question. What is the center? Remember, it's x minus y minus z minus. So it's going to be -4, 4, 2, x minus -4, y minus 4, z minus 2, and the radius.
6.
Do I square 36? No, I take the square root. That's it. Well, that's not too bad. So this is first day, Calc 3, and a lot of you are thinking, this is calculus? Well, we didn't do any calculus. We're not going to actually do any calculus for a little while. We're going to establish all of the rules for everything vector. Then we can start answering questions using vectors, and vectors are going to be a primary tool to answer questions. One of the coolest things we're going to do, and I'm pretty sure we're going to be back in the classroom by then, we're going to talk about basically flying through space, motion through space. And how do you describe motion through space? It's not how you think. And it is all done with vectors. And some of the stuff we're going to do is really cool. Then we can describe things like velocity and acceleration and curvature and all these really interesting properties. Basically, we can describe all motion from anything, you know, airplanes, cars, doesn't matter. We'll be able to describe motion, and we'll be able to analyze. We'll be able to do everything there is vector related. That's roughly the first month of the course. And for most people, they're just not very challenged. Now, if you've had physics, you've had a lot of exposure to this, but there's probably some bad habits that you got built in. There are things that people will do that you can't do. But I got the right answer. Yeah, but you divided by 0 and multiplied by infinity along the way. I want your vector understanding to be flawless. You know, the answers are going to be right because you're going to do good work mathematically, but I want you to understand everything you're saying. My experience over the years has been the people that wait to take 195, actually the people that waited till Calc 3 to take 195 always tell me they understood it better than any of their classmates, hands down, because they now had the vector background in a math class before they got to the physics. The thing is, you don't want to learn your math in the physics class. It's kind of like if you take chemistry at Mesa College, you can take chemistry at Mesa having had only remedial algebra. The problem is you do logarithms in chemistry. You don't do logarithms in remedial algebra. So you can be learning your logarithms in chemistry. That's a bad way to go. You want to learn your logs in math and then go to chemistry. None of you would learn your Spanish from me. You don't want to learn your math in the lab science. You kind of want to have the math set before you get there. But unfortunately, the way we do things, a lot of people are learning their math in the physics. And it's not the physics teacher's responsibility to teach you the math. They're assuming you already know it. So they'll give you everything you need to answer the questions, but you might not understand what you're doing or the why. Now, on the notes part of Canvas, now I'm gonna do a little share screen with you here. And here we go. But first of all, when we go to the module, okay, you got a lot of stuff under the notes. And schedule, for example, we will never deviate from this, not even a little bit. I know exactly how long everything takes because I've done it 10,000 times. So you notice today was introduction, vectors in 2D, vectors in 3D. Hey, that's what we did. Then dot product, cross product, and so on. On Monday next week, you see quiz 1. This is real simple. Lecture 1 is quiz 1. Lecture 2 is quiz 2, and so on, and so on, and so on. There's exactly 25 lectures in the course. And hey, what do you know? There's exactly 25 quizzes in the course. Every single lecture will have a quiz associated with the lecture that will look like the stuff we did. And if you're practicing the problems in your textbook, it will look just like the problems. And hopefully it's something that's really easy for you to do. And because the quizzes are always posted at least a week ahead of time, you have all the time in the world to look at them and get them right. You can ask me questions. What you can't do on the quizzes is get external help. It's got to be your work. But to be honest with you, you're supposed to get 100% on every single quiz because every quiz question that I ask you, I've already done that question in class in tremendous detail with explanation. So you're never going to see a quiz question that we didn't do. So you shouldn't need to get help on quiz questions. You want to really get good at those. And the other thing is, some people had a really hard time when they were doing their math classes asynchronously over, the last couple of years, and people would go to the internet to get all their answers. Now, I do want to warn you, that's considered plagiarism. Plagiarism is the highest form of cheating. Plagiarism doesn't come with a warning, it comes with expulsion. Okay, if you plagiarize on the college campus, your academic career pretty much could be over. Never do that. Why is it plagiarizing? Because you turned in a problem and you took credit for the work when it was somebody else's work. That's the definition of plagiarism, taking credit for somebody else's work. If you're getting it off the internet, it's not your work, it's somebody else's. You can't take credit for it. That's actually illegal, not just unethical. So I have to remind people. Now, if you don't know how to do something, just ask. Now, you guys are in an awkward position from a standpoint of tutoring, in that you're near the top of the food chain in terms of mathematics. So getting help, once you get Calc 3 and above, getting help from the tutoring lab gets harder, because when you go to the tutoring lab, often you're going to see your classmates, or worse, you're going to see people in a lower class than you. It's hard to find people that are higher than you on a regular basis, because that means that they've already had all the math classes and they're still at Mesa College. Now, I do know of a few tutors who had all this stuff with me last year, and they're still around, but there are not a lot of tutors who have already succeeded at the Calc 3 and the linear algebra and the differential equations and so on. Why? Because they've transferred. So this semester, you will have a lot of very good tutors who have been in the higher level classes. A lot of them are the peer mentors too, by the way. Now, I want to go over some of the notes. For example, you see vector worksheet. This is something you're going to do at the end of the week. This is just a worksheet. This isn't something you're going to turn in. Like here, vector rules. In a physics class, they don't go over this kind of stuff with you, but I go over some of the details. It's the do's and don'ts, what you can do with a vector. For example, a vector cannot appear in a quotient. Mathematically, that's an impossible statement. A lot of people will try to do vector quotients. It's an absolute mathematical law that anything that can appear in a numerator can also appear in a denominator. There's no such thing as exception. You say, but what about a zero? Yeah, if I have a zero in a denominator, we say the quotient's undefined. If I have zero in both numerator and denominator, we say it's an indeterminate form, but I can still do it. A vector cannot appear in a quotient because that would mean it could also appear in a denominator, and that would also mean there's something called a reciprocal of a vector, of which there isn't. A vector cannot appear in a function. So right here, I said there's no sign of the vector, or e raised to the vector, or a vector raised to the third power. Vectors are very limited in what you can do. So I go over some of the rules. Now, one of the things that I don't do, because I'm a math person, being a math person, I never use the IJK notation in vectors, ever. Never have in my life, and I would have the good fortune of never having an instructor at any level, even physics, back then, who use IJ and K. The problem with IJ and K is the ambiguity. It doesn't distinguish what dimension you're in. You use the same dimension, you'll write the same thing for 2 dimensions as you will for 3. Plus, in mathematics, I always means the square root of -1. There's no time that I means something other than the square root of -1. And when you get to linear algebra, you will do vectors with complex numbers, meaning you'll do vectors with i's in them. So having I be a vector and I be an imaginary number at the same time in the same statement can get a little confusing. I'm not a fan of the IJK notation for another reason. I teach mathematics at much higher levels in Calc 3. Vectors have no limit on the number of dimensions. IJK notation only works in 3. And those in linear algebra understand you're going to be 4, you're going to be n. There's no limit to the number of dimensions, but IJK is only in 3. Technically, you're not even supposed to use it in 2. So the problem a lot of us experience, oops, I'm going to do my erasing here. The problem a lot of us experience with the IJK notation is the problem of ambiguity, because a lot of times we write things that make no sense. If I write, I'm a math guy, that means 4 times the square root of -1. But some people say, no, I mean that to be a vector. Well, what vector would that be? Is that 4 times the vector 1, 0? Or is that 4 times the vector 1, 0, 0? Because those are very, very different. That's 2 dimensions, that's 3. And people who use IJK will write this for both of them. And you cannot represent vectors in different dimensions the same way. That's an absolute impossibility. So again, I'm not a big fan of that. And by the way, if you're doing it as a vector, you kind of need to indicate it's a vector, not square root of -1. You say, what about J and K? J in engineering is the same as I in math. J in engineering means square root of -1, and K in mathematics means curvature. It's something we're going to be doing with vectors. We use the I and the K on a regular basis in a mathematical class in vector context to mean things that are not vectorish. So I don't use that anymore. Now, in your physics class, use whatever they tell you to use. But in a math class, I prefer you write vectors in vector form. You know, little brackets with numbers in them. It just makes it cleaner and easier for all of us to understand. All right, now I'm going to stop there.